Okay, so this is number 20 from your quiz, and I'm not gonna lie, I have struggled with this one, and I don't know how well I'm gonna be able to explain it to you guys, but here I go anyway. So I need to draw a picture. I forgot to do that. I'll just do that right here. This picture was provided to you guys, so don't worry about that part. But so we have a mass here. There is friction going to the left, and we are told that that the magnitude of the frictional force is 80 newtons. We have the gravitational force. It's written as W here, but I'm going to write it Fg, and we're told that this is 196 newtons. We also have the normal force. Oh, yeah, it's on a surface here. So we have a normal force, which we are not given the value, and it is being pulled by the picture says P for pull. Wow, that makes sense. So I'm going to write it the force of pulling as FP. We're told this is 160 newtons, and that this force is at an angle of 60 degrees. So that's the situation we have. I will read the problem. A force P pulls on a crate of mass M that is in contact with a rough surface. Maybe I should write the surface then. Well, nah. The figure shows the magnitudes and direction of the forces that act on the crate in this situation. W, this, represents the weight of the crate. Fn represents the normal force on the crate, and F represents the frictional force. So one thing that I do want to point out already here, it's not really important, but I do want to point it out, is that these values, this friction is 80, right? That's positive 80. 160, the pulling force, that's 160. So it's kind of confusing because usually in our problems, we usually set one direction as the positive, usually right being positive and up being positive. So it's kind of weird, like you think, wait, shouldn't this be negative 80? And you're correct, it should be negative 80, but the reason why we're not being told it's negative is because I said it, but the figure shows the magnitudes and direction of the forces. This is just the magnitude of the frictional force, meaning it's not considering the direction, but ultimately, yeah, we do want to be aware that it's going in the opposite direction that we are pulling. Okay, so let's look at the question. Which statement best describes the motion of the crate? And this is a very theoretical question, and I don't like these, but let's try and see if we can figure this out. So the crate must be at rest. Rest means that the velocity is 0, right? The crate must be at rest. Do we have any information to tell us whether or not what the velocity is, or maybe even the acceleration? We don't know. They didn't give us any of those values. We don't know about acceleration. We do, well, things they did give us was the forces. And now, before I move on, I want to talk to you a little bit more about these forces that we have here. Because usually when we see forces, we always want to have them in the vertical component and the horizontal component. We do not like anything diagonal at an angle. We don't like that. Hopefully by now you know that when we do have a diagonal force, like the pulling force right here, we want to, I don't know if divide is the correct word, but we want to look at the force from its horizontal, the x component, and the vertical, the y component. So I'm going to divide this, there has to be a better word. Anyway, this pulling force into its horizontal and vertical components. So this horizontal would be Fpx, and the vertical would be Fpy. Now, say, ooh, what's happening? Sorry. We don't know what Fpx is, right? What if it's like, what if it's 100 newtons? I'm just saying, what if? If you look at our horizontal forces, the right side is 100 and the left would be negative 80. 100 is bigger than negative 80, so if it was 100 newtons, we can say that the mass is moving to the right. But we don't know that. So we actually need to calculate what Fpx is, and we can do that because they gave us enough values. So this is using trig, Fpx. We have, I don't know if you guys can see it, but we have a triangle here, meaning we can use trig. It'd be cosine. So I can say that cosine of 60 degrees is use SOHCAHTOA. I'm not good at explaining that part, but if you can figure it out, please figure it out. Cosine 60 would be adjacent over hypotenuse. I hope we're good on that. And we are solving for Fpx, the horizontal pulling force. So I'm going to multiply both sides by Fp. So I just rewrite it as Fp cosine 60. Fp was 160 newtons. So 160 cosine 60 degrees. And I don't have my calculator with me right now, but I do think this just turns out to be 80. So this is 80. What does that tell us? That tells us that horizontally, we have equal forces pulling on this mass. It's pulling 80 to the right and 80 to the left. That means when we're not moving, is what we're saying. I can go into more detail. So you guys know the equation F equals ma. The forces that we have, the net force we have, if we set right as positive, which I think we already did, but if we set right as positive, we just say 80, because that's going to the right, minus, well, it'd be plus, because it's net, but plus negative 80, going to the left, right? That'd be our equation. Now, that just turns out to be 0 equals ma, which means that our acceleration is 0, meaning we're not accelerating. Oh no, did I say that we're not moving? Delete that from your brains. I didn't say that. That's incorrect. I didn't say we're not moving. The correct way to say is that we are not accelerating. That is a very important distinction, and I do think I said we're not moving, and that's incorrect. Sorry, delete that. Sorry, we don't know if we're not moving or not. We just know we're not accelerating. So, going back, the crate must be at rest. I don't know. I don't know. So I'm going to write triangle next to A. I honestly can't remember what the answer is right now. So I hope I can find the answer by the end of this video. Oh gosh. Okay, B, the crate must be moving with constant velocity. So now we're being told there is a velocity. So do we know if we have a velocity? We don't know. They didn't tell us anything. we only know that acceleration is 0, but could we have a velocity while having no acceleration? Yes, we can have a velocity with no acceleration. And you can kind of see that in our kinematics equations. V final equals V initial plus AT. Say we don't have an acceleration. So that just becomes 0, right? Which just means V final equals V initial. That's just saying that we have we're in a constant state of motion, which, yeah. So I hope that makes sense. Let me go back to B. The crate must be moving with constant velocity. Honestly, I don't know. I'm going to put a triangle next to that too. C, the crate must be moving with constant acceleration. Finally, we, I hope by now, have established that A is 0. We have no acceleration. Could 0 be considered a constant acceleration? Okay, I don't want to go there, but I do think that C is incorrect because we don't even have an acceleration. Oh no. Okay, let's look at D. The crate may be either at rest or moving with constant velocity. We evaluated these two. At rest, that was A. Moving with constant velocity, that was B. I'm kind of not sure about that, so I'm going to put a triangle next to that too. Okay, let's look at E. The crate may be either at rest or moving with constant acceleration. I hope we can agree that we do not have a constant acceleration. So I'm going to say no to E either. So now we're kind of left with A, B, D. So let me see if we can figure this out. I did include here the 3 laws of Newton with a little picture I found on Google. I thought I could use these while explaining it, so let me see if I could get any hints from these. So first law of motion, an object at rest will remain at rest unless a net force acts on it. An object in motion will remain in motion unless a net force acts on it. Okay, Newton's second law, if you apply more force to an object, it accelerates at a higher rate. Newton's third law would be that force always come in pairs. You push on a wall, the wall pushes back. So, okay, I want to actually focus on to this picture right here. So, when there's an acceleration, the speed increases faster. Meaning, it might have been 0, but we can never say that we didn't have an initial speed here, right? This would be like VF. So there might have been a V initial. So that's kind of what I want to say here too. We don't have an acceleration, but we can't conclude that we didn't have an initial velocity here. We might have had it, we might have not. We're just not given enough information. And could this be at rest? Yeah, it could be. V initial might be 0, or it might be, I don't know, 10 meters per second. I don't know is the answer. So using those two I don't knows, I think the answer would be D. That is my guess. If anybody can check their Scantrons and tell me if you got it right, or maybe if you got it wrong. Maybe you picked D and it says it's wrong. Maybe I'm wrong. Who knows? But yeah, that's number 20.